In the following 15 minutes, I'd like to share with you our radar research at UMass Law. The topic of this research project is electromagnetic detection and identification of concrete cracking in highway bridges. Of course, this research wouldn't be possible without our graduate and undergraduate students. Dr. Student Sanjana Biniaka, Dr. Candidate Ahmed Alziadi, Dr. Jixiang Tang, Dr. Student Johnny Wang, and undergraduate student Ronan Bates. The problem we are trying to solve in this research is the use of radar to detect and quantify concrete cracks in concrete bridges. In the past, there are already existing technologies in the areas of structural health monitoring and non-destructive testing. And essentially, these technologies are categorized into the near field and or the far field. Basically, in order to get the subsurface information, near-field technologies are used, such as impact echo, ground-penetrating radar, ultrasonic testing, and the use of instrumented wireless sensors. For far-field technology like SAR, they are essentially used for the remote sensing purposes, like the inspection or profiling of a surface terrain or surface texture determination. Our approach is to use the remote sensing technology like SAR for subsurface sensing. And we plan to develop a data-driven field inspection procedure for the concrete crack detection and quantification for highway bridges. We will use radar images for detection and for quantification of concrete cracks. First, why electromagnetic sensors? They are efficient, they are non-destructive, and they are able to penetrate into dielectrics like concrete structures. And why synthetic aperture radar? Synthetic aperture radar is remote. It has a flexible resolution with the increase of center frequency, increase of bandwidth, as well as the increase of synthetic aperture. With these increases, a better resolution SAR images can be obtained. Now, electromagnetic sensors actually are not total strangers to civil engineers in the past. Civil engineers have been using electromagnetic sensors for material characterization, bridge pier scale detection, concrete void or crack detection, rebar detection in concrete structures, remote sensing, and even concrete cover inspection using different frequencies. In general, lower frequencies below 1 gigahertz are used for material property characterization, and higher frequencies above 1 gigahertz are used for crack detection or damage detection. In the problem of concrete crack detection, the way GPR detects a crack is by moving along the cross-range axis and to detect the reflected waves from the crack presence to the location of the radar. With the motion of the GPR, this distance is constantly changing. Eventually, the pulse radar, like GPR, will reconstruct a hyperbola, indicating the pattern of a crack in concrete structure. And this interface represents the dielectric discontinuity. On the other hand, the principle that synthetic aperture radar detects a crack is by superimposing and reconstructing the scattering patterns between the radar and the cracks. Therefore, rather than looking at only the first interface between the crack and the radar and the concrete, SAR actually can see both the front and also the back of the crack. If we want to use radar sensors for subsurface sensing of concrete structures, the first question popping into mind is how deep can this radar signals penetrate into concrete? And the parameter usually used for answering this question is what we call penetration depth, delta. Now, to scientifically answer this question, we need to know not only the frequency used, but also the materials property, such as electrical properties and magnetic properties of concrete. Electrical properties of concrete can be affected by the water-to-cement ratio, porosity, moisture content. Magnetic properties of concrete can be affected by the type of coarse aggregates in concrete. Another question we also want to know is how can we learn from SAR images? If there's a change of materials property as well as the change of structural geometry, they can be reconstructed in SAR images. The challenge for researchers to solve is how do we differentiate the change in materials property from the change of structural geometry? On this concrete crack detection problem, There are also other challenges as well. The first challenge is the quantification of random and semi-random crack geometry. We know that real cracks do not have regular geometry. They don't have uniform concrete crack widths. They don't have constant crack depths. They don't even have a regular crack surface. So the first question we have to answer is how to quantify real cracks in concrete structures. Change of moisture content in concrete will also influence the SAR images of concrete structures. So we also have to study that how does moisture level in concrete affect the radar images of concrete. The last challenge is even we perform a lot of laboratory study. When we apply this kind of non-destructive testing technologies to real structures, it is usually unable to non-destructively verify our inspection result. Our approach is to use a continuous wave synthetic aperture radar sensor at 10 gigahertz. To conduct the research, we start with laboratory concrete specimen. We have cast the concrete specimens with non-cracked geometries and condition them in a room environment. And the reason we choose the dimensions of these concrete specimens is because if the concrete specimens are too small, we do not have enough background signal to model. If the concrete specimens are too big, we cannot handle them in monitoring their moisture change. To determine the moisture effect on the SAR images of these concrete specimens, we first place these concrete specimens inside the water tank to achieve 100% saturation. After that, we took the specimen out of the water tank and placed them in the room condition and to let the room to slowly dry out its moisture. And after 5 months of time, we also place these concrete specimens inside the oven in order to get oven dry mass of this concrete specimen. While we are monitoring the change of the moisture, we also scan these concrete specimens with our continuous wave synthetic aperture radar imaging sensor. By doing so, we can develop a radar image database. And with all this database, we can extract patterns from radar images. So shown here are examples of SAR images of 4 concrete panels. We can see that the increase of moisture not only will change the amplitude of SAR images, but also the distribution. After successfully developing these radar images of concrete specimens at different moisture levels, the next thing we did was to model the change in the SAR images with the moisture content quantitatively. We also have found that the integrated SAR amplitude and the average maximum SAR amplitude are exponentially related to the moisture content inside the concrete. Besides the amplitudes in the SAR images, we also noticed that the distribution of the SAR amplitudes also indicates the presence of a crack in concrete. In the front of this contour area, we noted there is integrated front scattering response representing the presence of a surface crack. In the back, there's also back scattering response. And among these two, the back scattering response shows much more significant change. We also try to quantify this shape change. And in the past, we have developed a new approach. It's called KRI, representing for curvature area ratio and SAR amplitude transformation. This transformation is essentially to convert a 3-dimensional SAR image into a 3-dimensional curve. Once we have the 3-dimensional curves, we can quantify these curves by comparing the covariance between 2 3-dimensional vectors. From this comparison, we notice that the area ratio and SAR amplitude curves at different moisture levels give us useful information for crack detection. In the upper left corner, in saturation state, the presence of a surface crack can actually increase the area of contour. However, this trend is reversed when there's moisture loss. Our explanation is this. In saturation, the increase of that concrete dielectric constant makes concrete become a stronger reflector, increasing the SAR amplitudes of the concrete specimen. When the radar signals enters the crack, the multiple reflections of radar signals inside the crack due to the saturated concrete dielectric constant can also increase the amplitudes of SAR images. When the concrete is moist, the surface is dry. The moisture distribution is non-uniform. Porosity of concrete makes concrete surface become a very good absorber. The presence of a crack actually provides more surface area to absorb these incident radar signals. As a consequence, the cracked concrete in moisture state will actually have a less response, leading to the reduction in the SAR amplitudes. For practical applicability, we also compare SAR imaging results with the GPR imaging results. In this slide, we show the same concrete specimens scanned by a 1.6 gigahertz GSSI structure scanned portable GPR. We can see that from the B-scan image shown in this slide, the presence of a surface crack will lead to the reduction of the signal. After the removal of the background signal, a hyperbola pattern can be found. And this hyperbola represents the characteristic geometry of these cracks. Now let's compare GPR B-scan images and SAR images. We have learned that the presence of a surface crack can lead to the reduction of GPR images from the previous result. And the presence of a surface crack can also lead to the reduction of SAR images. From here, we learned that this is only true when the concrete is not saturated. Consistency can be found in this comparison between GPR and SAR. Another comparison we also did was to extract the hyperbolic pattern of GPR B-scan images representing the presence of a surface crack with the SAR images. We convert the SAR images contour curve into a angle and distance representation. From this representation, the fluctuation of contour area can actually be illustrated in a similar fashion with the GPR B-scan hyperbola pattern. From here, we have learned that the presence of the crack can increase the envelope area of hyperbolas from the background subtracted GPR B-scan images. We conclude that the envelope area of a hyperbola in background subtracted B-scan images is related to the crack volume. We have learned that the greater the crack volume is, the greater the envelope area in the hyperbola of a B-scan image. On the other hand, for SAR images, there's no need to perform background subtraction. What about the practicality? In the past, we started from the laboratory concrete specimens inside an electromagnetic anechoic chamber built at the UMass store. And we have converted this laboratory system into a portable SAR imaging system and use it in the past. And we also have converted this portable SAR imaging system into a more compact portable system. The difference between laboratory concrete specimens and the real concrete structures is the boundaries. Laboratory systems are with finite geometries, therefore the contours are usually closed. However, when we apply SAR imaging on real structures, you can also see that we will still be able to extract a closed contour, even the boundaries are infinite to the radar. From our previous field inspection results, we have learned that the presence of a surface crack can actually reduce the amplitude of SAR. We also have learned that this is because all these concrete structures are not saturated. If we look closer, we can even notice that the presence of the crack in the subsurface rebars and also other surface geometry can be revealed in the SAR image. The questions we want to answer regarding the field applicability of SAR imaging is because there is no way we can actually determine the actual moisture content of real structure. We need to have a pattern recognition algorithm to determine the physical meaning of this amplitude. And the approach we propose is to use the surface amplitudes to relate it to the subsurface moisture content, which is an ongoing work taken by my group. In conclusion, we believe that electromagnetic sensors can detect changes in materials properties and structural geometry of concrete structure. And we also have demonstrated that both the 1.6 gigahertz GPR and 10 gigahertz SAR sensors can detect a 0.5 centimeter width concrete of different depths and also different widths. Background subtracted GPR B-scan images usually are used to reconstruct the hyperbolic pattern of electromagnetic scattering signals due to the presence of a crack in concrete. And the envelope area of this hyperbola represents crack volume. What we propose to achieve is to develop a portable SAR imaging sensor to detect and to quantify concrete cracking. From our research, we believe that monitoring the background signal change, including such as moisture, is essential for the crack detection on concrete bridge. SAR imaging can also provide quantitative moisture content if there's no crack, which means we can use the same technique on intact area of a concrete bridge to determine the moisture content first, and then use this knowledge to detect and use this knowledge to quantify subsurface crack. At last, we must acknowledge the financial support from TIDC and the help from other people, former master students Harsh Gandhi and director of laboratory Gary Hall at UMass Law, and they help us with the laboratory and field tests. Their assistance are greatly appreciated. With that, I will close my presentation and open for questions. Thank you.